الرحمن الرحيم. Let us start topic number 3 in our chapter Distribution and Network Models. In this topic, we will consider together a transshipment problem. In topic number 1, we consider a shipment model. In topic number 2, we explain the assignment model as a special case of the shipment model. In this topic, we will consider a general case of a shipment model. This is a transshipment problem. In the transshipment problem, we will have 3 types of nodes. Source or supply node, destination and or demand nodes, and this we will consider in a shipment problem. Beside these 2 type of nodes, we will have a transshipment nodes. The transshipment problem is an extension of the transportation problem, where there will be an intermediate nodes. We will refer to it as transshipment nodes, such as warehouses. To imagine this, let us say that we have plants, distribution centers, and warehouses. By this way, the products will be shipped from the plants to the warehouses, and from the warehouses to the distribution centers. This network model is a more general model, as the shipment of goods may be made between any pair of the 3 general type of nodes. The 3 general type of nodes are origin nodes, transshipment nodes, and destination nodes. As a model, we can ship from the origin to the transshipment and ship from the transshipment to the destination. Also, we can ship from the origin to the destination directly. or we can ship from origin to another origin, or from transshipment to another transshipment node, or from any destination node to any destination node. So we can say that the transshipment problem permits shipment of goods from origin to intermediate nodes, or from the intermediate node to the destination, or from one origin to another, or from one intermediate location to another, or from one destination location to another, or directly from the origin to the destination. To explain this, we will consider our example as follows. Before any of the transshipment problems, such as a shipment problem, the main objective function may be cost minimization or profit maximization, and there will be a constraints. The constraints can be classified into three types of constraints. Constraints reflect the relationship between the origin and the transshipment. Constraints reflect the relationship between the transshipment and the destination. The first one is a supply constraint. The last one is the demand constraint. Besides these two types of constraints, we will have a constraint which reflects the relationship between the transshipment nodes and the supply node and the demand node. Of course, in our transshipment problem, the supply available at the origin will be limited, and the demand at each destination will be specified. The objective function, cost minimization or profit maximization. This means that we want to determine how many units should be shipped over each arc in the network, so all destination demand are satisfied with a minimum possible transportation cost or with a maximum possible profit. In our example, we will assume that we have two plants. Ryan is an electronic company with production facilities in Denver and Atlanta. Plant at Denver, another plant at Atlanta. Component produced at either facility may be shipped to either the firm's regional warehouse, which are located in Kansas City and Louisville. This is the transshipment nodes, Kansas City and Louisville. 2 plants, 2 transshipment. From the original warehouses, the firm supplies retail outlet in Detroit, Miami, Dallas, and New Orleans. This means that we will have 4 distribution centers. The transportation cost per unit from each plant to each warehouse and from each warehouse to each retail outlet is as follows. Transportation cost per unit from Denver to Kansas City, $2. From Denver to Louisville, $3 per unit. From Atlanta to Kansas City, $3. From Atlanta to Louisville, $1. Transportation cost from warehouses to retail outlet from Kansas City to Detroit, $2 per unit. To Miami, Kansas City, Miami, $6 per unit. Kansas City, Dallas, $3 per unit. Kansas City, New Orleans, $6 per unit. From Louisville, transshipment node to Detroit, $4. To Miami, $4. To Dallas, $6. To New Orleans, $5. The key features of the problem are shown in the network model specified in the following figure. In this figure, we will use circle to represent the nodes, arc to represent the relationship between them. Note that the supply at each origin and the demand at each destination will be shown in the left and right margin respectively. Let us display our network. We have 3 plants: Denver, Atlanta. 2 plants, we have 2 plants, Denver, Atlanta. We have 2 transshipment warehouses, Kansas City, Louisville. We have 4 distribution centers, Detroit, Miami, Dallas, and New Orleans. Note that in the shipment problem at topic 1, we numbered the origin and destination separately. We number them 1, 2, 3, 4 and number the other 1, 2, 3, 4 also. But here we number all the circles sequentially 1, 2, 3, 4, 5, 6, 7, 8. Plant origin, warehouse transportation nodes, retail outlet distribution centers, or destination nodes. According to our transportation costs, there will be a shipment from Denver to Kansas City. There will be shipment from Denver to Louisville, from Atlanta to Kansas City, from Atlanta to Louisville. It means we will ship our goods from the plant to warehouses and from the warehouses to the retail outlet. The supply at the plants are as follow: 600 unit Denver, 400 unit Atlanta, 600,000, 400,000, whatever. This is the supplies. The demand, 200 unit for Detroit, 150 unit for Miami, 350 unit for Dallas, 300 unit for New Orleans. Note that the sum of the supplies, 1,000. The sum of the demand, also 1,000. Let us complete our network by drawing the arrows. We will ship from Denver to Kansas City. Ship from Denver to Louisville. Ship from Atlanta to Kansas City. From Atlanta to Louisville. Then, the good will be shipped from Kansas City to Detroit, or from Kansas City to Miami, or from Kansas City to Dallas, maybe from Kansas City to New Orleans. The same from Louisville to Detroit, from Louisville to Miami, from Louisville to Dallas, from Louisville to New Orleans. Cost of shipment will be displayed on the arrows, on the arcs. $2 per unit from Denver to Kansas City, $3 per unit from Denver to Louisville, $3 from Atlanta to Kansas City, $1 from Atlanta to Louisville, $2 from Kansas City to Detroit, $6 Kansas City, Miami, $3 Kansas City, Dallas, $6 Kansas City, New Orleans, $4 Louisville, Detroit, $4 Louisville, Miami, $6 Louisville, Dallas, $5 Louisville on New Orleans, destination route and transportation cost per unit. As we mentioned before, the supply constraints must be smaller than or equal. The demand constraints must be equal. Don't forget this. In addition, we can count the cost of transportation by considering or by using the cost per unit on the arcs. This is our model again. And let us express our objective function and constraints. To identify our objective function and our constraints, we have to use the subscripted variable xij. Xij in this case will be as follows: x13, x14, x23, x24 to represent the quantities which will be shipped from the plants to the warehouses. Then x35, x36, x37, x38, and x45, x46, x47, x48 to represent the quantities which will be shipped from the warehouses to the retail outlet. Okay? As the transportation and the assignment problem, we will use xij to represent the number of units shipped from node I to node j. As I mentioned, x13 denote the number of units shipped from Denver to Kansas, from Denver plant to Kansas City warehouse. x14 number of units shipped from Denver plant to Louisville warehouse, and so on. Because the supply at the Denver plant is 600 units, the amount shipped from the Denver plant must be less than or equal to 600. And also because the supply at the other plant, Atlanta, 400, also our constraints of supply for Atlanta smaller than or equal to 400. Mathematically, we can write it as follows: x13 plus x14 smaller than or equal to 600, and x23 plus x24 smaller than or equal to 400. This is the two supply constraints. Also, the demand constraints also, the demand constraint will be equal to, return back to our graph, we can say x 3, 5 plus x 4, 5 equal to 100, x 3, 6 plus x 4, 6 equal to 150, x 3, 7 plus x 4, 7 equal to 350 equals x 3, 8 plus x 4, 8 equal to 300. This two type of constraints is the same as the shipment. What is the difference between the shipment and the transshipment? The shipment and transshipment difference located at these two circles. Why? Because these two circles are intermediate. Kansas City and Louisville warehouses, intermediate nodes. So, the amount of goods which will ship from Denver to Kansas City and shipped from Atlanta to Kansas City must be equal to the quantity of goods which will shipped from Kansas City to Detroit, Miami, Dallas, and New Orleans. Also, the quantity of goods which will shipped from Denver, to Louisville, and from Atlanta to Louisville must be equal to quantity which will be shipped from Louisville to Detroit, Miami, Dallas, and New Orleans. This is the difference. This is the additional constraints beside the supply constraints which we mentioned and the demand constraint which we mentioned. There will be the transshipment constraints. It will be as follows. We now consider how to write the constraint corresponding to the two transshipment nodes. For node 3, Kansas City warehouse, we must guarantee that the number of units shipped out must be equal to the number of units shipped into the warehouse. As follows. Number of units shipped out of node 3 is x35 plus x36 plus x37 plus x38. And the number of units shipped into node 3 will be x13 plus x23. the first expression must be equal to the second. This will be as follows. x35 plus x36 plus x37 plus x38 equal x13 plus x23. The same for constraint corresponding to node number 4. x45 plus x46 plus x47 plus x48 must be equal to x14 plus x24. The destination nodes constraint we mentioned before, it will be as follows. x35 plus x45 equal to 100. Similarly, x36 plus x46 equal 150. x37 plus x47 equal 350. x38 plus x48 equal 300. Then our objective function. As usual, the objective function reflects the total shipping cost over the 12 shipment routes. As we mentioned before in topic 1. By this way, our model will be a combination of the objective function and the constraints for 12 variables, 2 plant times 2 warehouses times 4 destination. We will have 8 constraints. 2 constraints for the supply, 4 constraints for the demand destination, and 2 constraints for the warehouses. Our model by this way will be as follows. Minimize 2x1 to x13 plus 3x14 plus 3x23 plus 1x24 plus 2x35 plus 6x36 and so on, subject to x13 plus x14 smaller than or equal to 600, x23 plus x24 smaller than or equal to 400, transshipment constraint minus x13 minus x23 plus x35 plus x36 plus x37 plus x38 equals 0, minus x14 plus minus x24 plus x45 plus x46 plus x47 plus x48 equals 0. x35 plus x45 equal 200. x36 plus x46 equal 150, and so on. By solving this model through the management scientist application, we will get the following computer solution. This is the model. And this our solution. Objective function value 5,200. Cost of shipment x1 3 equal 550, x14 equal 50, x23 equal 0, x24 equal 400, and so on. And there is a reduced cost and the model. A summary of this model. A report of this model can be represented as follows. Routes from Denver to Kansas City, from Denver to Louisville, from Denver to Atlanta, from Atlanta to Louisville, from Kansas City to Detroit, Kansas City to Dallas, Louisville, Miami, Louisville, New Orleans. Unit shipped and cost per unit, and the total cost and the sum of the total cost. We may ask you about this report. We may give you the computer solution as shown in this transparency, in this slide. And then ask you to prepare a report. How many units will be shipped from to, and how much the cost. This will be the report. We may also ask you to prepare the transportation network. It will be a graphical representation of this report or a graphical representation of this optimal solution. As mentioned at the beginning of this section, we said that ARC may connect any pair of nodes. In the previous example, we solve it as a traditional example. What we mean by traditional example, shipment from plant to warehouses, and then shipment from warehouses to retail outlet. Shipment from origin to intermediate, then from intermediate to destination. Now we will consider transshipment from any arc to another, from any node to another. It means all such shipment patterns are possible in the transportation problem. We still require only one constraint per node, but the constraint must include a variable for every arc entering and every arc leaving. Let us consider this by saying the following. For the origin node, the sum of shipment out minus the sum of shipment in must be less than or equal to the origin supply. These are our rules. For the destination node, the sum of shipment in minus the sum of shipment out must be equal to the demand. For the transshipment node, sum of shipment out must be equal to sum of shipment in, as we mentioned before. Don't forget these three rules. For the origin, sum of shipment out minus sum of shipment in smaller than or equal. For the supply, for the destination, for the demand node, sum of shipment in minus sum of shipment out must be equal. For the transshipment, sum of shipment out must equal to sum of shipment in. Let us consider this by the following example. Let us modify the Ryan electronic problem and assume that it is possible to ship directly from Atlanta to New Orleans at $4 per unit and from Dallas to New Orleans at $1 per unit. This is the modification which we will do on our example. The network model which corresponding to this modification will be shown as follows, and the linear programming formulation will be next. Denver, Atlanta, Kansas City, Louisville, Detroit, Miami, Dallas, New Orleans. Plant, warehouses, retail outlet, 600 supply, 400 supply, demand 200, 150, 350, 300, demand, the arcs as we mentioned the same, this is our original model. We will make two modifications. Number one, we will permit transshipment from Atlanta to New Orleans with a cost $4 per unit. And we will permit shipment from Dallas to New Orleans This is our original. The modification permit shipment from Atlanta to New Orleans. Another modification by $4. Second, permit shipment from Dallas to New Orleans for $1 per unit. This modification require modifying our mathematical model, our linear programming model. First modification, there will be x to 8 additional variable. And there will be x78 additional variable, decision variable. The modification in the objective function will be 4x to 8 added as a cost of shipment and 1x78 to represent the quantity which will be shipped from Atlanta to New Orleans, x to 8, and the quantity which will shipped from Dallas to New Orleans, x78. Besides, the quantity which will go into Dallas minus the quantity which will get out of Dallas must be equal to 350. This is another modification. This is our model again. Our objective function will be as follows. Minimize 2x13 plus 3x14 plus 3x23 plus 1x24 plus 4x28 plus 2x35 plus 6x36 plus 3x37 plus and plus x1 x78. In the previous figure, we added two new arcs to the network. These two new variables are necessary in the linear programming formulation. The next figure shows that new variable x28 and x78 appear in the objective function and in the constraint corresponding to the nodes to which the new arc are connected will be as follows. Look to constraint. Of the supply x37 plus x47 minus x78 equals 350. For the constraint x23 plus x24 plus x28 smaller than or equal to 400, x to 8 input into the objective function for x to 8 plus 1x78 additional to variable with cost coefficient in the objective function. Also, we can solve this problem by using the management sign test. The following computer solution will show that the value of the optimal solution has been reduced $600 by adding the two new shipping routes. X to 8 will be 250 units are being shipped directly from Atlanta to New Orleans, and X7 will be 50 units are being shipped from Dallas to New Orleans, and our cost will be reduced by $600 as follows. Our objective function value 4,600 instead of 5,200, $6 less, and there is x to 8 250, x7 8 50. This is a modification of the model. Such as the shipment problem, the transshipment problem has a problem variations. 4 variations will be considered. Total supply not equal to total demand. Maximization objective function instead of minimization. Route capacity or route minimum. Unacceptable routes. How we can solve this variation? The same as we mentioned before. It means if the supply is greater than the demand, there is no problem. If the supply greater than the demand, there is no problem, because the supply is smaller than or equal. But if the demand greater than the supply, there is a problem. How we can solve it? By adding dummy supply nodes with the difference between the supply and demand, as we mentioned. Maximization, no problem. The objective function will be changed from minimize to be maximize. Route capacity can be added as a constraint. Unacceptable routes, it means we have to drop the arc between the two nodes, which is unacceptable routes. The linear programming model modification required to accommodate this variation are identical to the modification required for the transportation problem. When we add one or more constraint of xij smaller than or equal to show that the route from node I to node j has capacity, we refer to the transshipment problem as capacitical transportation problem. The general linear programming model: xij number of units shipped from node I to node j, Cij cost per unit shipped from node I to j, Si supply at origin node I, dj demand at destination j. The general linear programming model for the transshipment problem will be as follows. Minimize all arcs, sum of Cij xij, subject to sum of arcs minus sum of arcs in minus sum of arcs out minus sum of arcs in smaller than or equal to Si. Origin node, sum of arc out, sum of Xij arc out equal sum of arc in Xij transportation node, sum of arc in Xij minus arc out Xij equal Dj, destination node, Xij greater than or equal to 0 for all Ij. By this, we finished our chapter 6, network and transportation model. Best wishes and thank you, and we will meet in the next chapter 9. Thank you.